Hello all, welcome to this course on time series modeling and forecasting using R. Now we are almost midway this week, and again, as probably all of you know, that the broad idea that we are talking about this week is how do you capture volatility and what exactly are the different models to capture the volatility which is sort of persistent in an underlying time series. And again, if you vaguely remember, just to sort of again brief you as to what we covered in the last lecture, is that we talked about one particular very important model called as ARCH, or in short ARCH, and then the full form is auto-regressive conditional heteroscedasticity. Okay. Now again, as all of you might know, that heteroscedasticity, this term means that changing variance. So the entire idea is, rather than focusing more on how do you capture the mean aspect of the time series, we will try to capture the variance, or we will try to capture the volatility in the underlying time series. And again, as a brief reminder, just in the last session we talked about a generalized arch model, let us say with certain order m, and further we wrote down a particular arch model, let us say with an order of 1, and there we wrote down its model structure and then a couple of properties about that and so on and so forth. Okay. Now this is again a new session this week, and then the very first thing we will do this week is how can one test for the arch effect. So again, if you remember vaguely, we discussed even in the last lecture that before you try to model using any volatility models, we have to first ensure that the underlying residuals, they contain some arch effect. So arch effect means that the underlying residuals, do they have changing variance properties? I mean, again, if the underlying residuals do not have a changing variance properties, then it is of no use to sort of capture and focus on the variance aspect, right. So in order to ensure that the underlying residuals which come from the mean equation have some arch effect, or rather they sort of exhibit the changing variance property, we have to actually formally test that. Okay. And this is the exact same thing that we will do now. So the very first test we will discuss is called as the LM test, and again this is a very famous test. So the full form is Lagrange multiplier test, or in short LM test, or in short you can see that in some textbooks it is referred to as arch test also. So the whole idea is that you have to implement this LM test to sort of confirm that the underlying residuals that you get from the mean equation contain the arch effect, or in other words they exhibit some changing variance pattern. Now again, one small point to mention before we start with anything new here is that how do you model the mean structure. So we tend to model the mean equation by all the usual models we have studied so far. So let us say ARMA, AR, MA, ARIMA, etc. Now again, in the last session we sort of walked through the rough steps as to how do you sort of model the volatility of a time series. So the very first thing is to sort of model the mean equation. So using ARIMA model and so on and so forth, then you sort of extract the residuals from that mean modeling, and then if the residuals show some changing variance behavior or changing variance aspect, then we say that you have to apply some ARCH or GARCH or its extensions on that. Okay. Alright, so now again, how do you test that? So the first test, again just to summarize, is called as the LM test. So the Lagrange multiplier, or in short LM test, also called as the Engel's arch test. So by the way, this was developed by Engel, it is called as Engel's arch test, is a commonly used test for detecting the arch effects. Okay. And exactly we will study that what this test involves, and then what are the following steps. Okay. So the test involves the following steps. So the first thing, as we talked about a short while back, is that estimating the mean equation. Alright, and for that you have to sort of fit a model, let us say ARMA, ARIMA, something like that, to the return series to get the residuals. Okay. So the very first step is how do you estimate the mean equation. So let's assume that you estimate the mean equation using an ARMA process, right. So you model the ARMA and then extract the residuals, right. So you model the ARMA to the return series and then get the residuals. And then what? So the second step is you square the residuals. Okay. So once you obtain the residuals from the mean equation, you square them. So square the residuals. So square the residuals from the mean equation to get a proxy for the variance at each point in time. Okay. So in short, this ET square, so when you take the square of the residuals, this would be kind of equivalent, not entirely of course, to the variance of the underlying time series, and then again we will show why exactly this is true. Okay. So the moment you square the residuals, it serves as a proxy to the variance at each point in time. So this is something like, so again we are assuming that variance of yt is sort of changing along with time. So you can write down something like sigma t square, and this Et square is kind of similar to the behavior of the variance term, which is sigma t square. Okay. So in short, the square of the residual proves to be a very important ingredient when you try to model the changing variance of a time series. Okay, then what? So, once you extract the residuals, then you sort of fit a very simple regression model. And how exactly? So, you regress the squared residuals on a set of its lags to determine if the variance at a given time depends on past residuals or not. Again, just to repeat, so once you extract the residuals and get hold of the residuals, then you create a very simple regression model. And how exactly? So, you regress the squared residuals on a set of lags to determine if the variance at any given time depends on some past residuals or not. And lastly, test for significance. So, the null hypothesis is that there are no arch effects. So, again just to summarize, if you write down H naught, then I can simply write down something like arch effect is not there, whereas the alternative hypothesis would be something like the arch effect would be there. Okay. So, once you sort of perform this test, you have to actually test it out, or rather test for its significance. So, the null hypothesis or H naught is that there are no arch effects, that is, no conditional heteroscedasticity exists. So, if the test statistic is significant, then arch effects are present. So, if you are able to reject the null hypothesis, which means that if the test statistic is significant, right, and you are able to reject the null, then we can sort of safely conclude that there exists some arch effects in the underlying residuals. Okay. So, in general, this LM test is not really difficult. So, what you do is you try to fit the mean equation using, let us say, ARMA model or ARIMA model and so on and so forth, and once you fit the mean equation to the return series, you extract the residuals, then you square the residuals, because squaring the residuals serves as a proxy to the underlying variance at each point in time. And once you square the residuals, you create a very simple regression model, where of course the dependent variable would be nothing but ET square. Okay. So, this regression model that we are talking about here contains the dependent variable to be nothing but the squared residuals. Okay. And what would be the independent variables? Independent variables would be set of lags to determine if the variance at any given time depends on some past residuals or not. And lastly, you simply test for its significance. Okay. Okay. So, again just to summarize all the steps, so the very first step is model fitting. So, let us say fit an ARMA model to the returns or residuals and obtain the residuals of that model, that particular ARMA model. Then second step is calculate the squared residuals, alright. Third is run a regression of the squared residuals on its lagged values, and this is in particular called as the ARCH1 model. Okay. And lastly, you simply test the hypothesis that the coefficients of the lagged squared residuals are 0 or not. Okay. Alright, so now the next section is again important as to how can one pick the optimal arch order. Okay. Now, again let me just very briefly go back to the last session where we discussed a general kind of an arch model, let us say a general arch model with order m, right. Now, again the idea is that how do you pick this order, right. I mean, how exactly do you pick the order optimally? So, would you say that arch 1 model is the best, or arch 2 model is the best, or arch 3 model is the best, right. So, there has to be some yardstick to sort of pick this general order m. Okay. So, this is a small description here that selecting the appropriate order for an arch model is a very crucial step in time series modeling. So, once you decide that okay, so there exists some arch effect in the residuals, and then you go ahead and then decide that we have to put forward some arch model or rather GARCH model on the residual data. But then the next question is how do you decide on its optimal order? Okay. So, hence selecting the appropriate order for an arch model is a very crucial step in time series modeling. The order of an arch model, typically denoted as Q, so let us say Q denotes the order of the arch model, represents the number of lagged squared residuals used to model the conditional variance. Okay. So, let us say if you assume that the order of this arch model is Q, so that letter Q determines the number of lagged squared residuals which are used in the model to model the conditional variance. Okay. Okay. So, of course, these are the steps as to how can you pick the optimal arch order. So, the very first step is perform an arch effect test, of course. So, before you actually go ahead and then try to fix some Q, you have to first confirm the presence of arch effect in the residuals of the time series model, and for this one can again easily use the LM test. Okay. So, confirm the presence of the arch effect in the residuals of the time series model, and for that we can use the LM test which was discussed just a short while back. Okay. Now, the next step is important. You have to always choose some initial order Q. Okay. So, let us say choose some initial order Q, and then use some information criteria, and then we well studied that what exactly are some of the well known information criteria, let us say AIC or BIC, etc. So, use some of these information criteria, let us say AIC or BIC, And what you do? Fit arch models of different orders and pick the best one corresponding to least AIC. Okay, so again, so I will say that the step 3 is kind of very easy. So it's not difficult at all. So what you do is you go ahead and then try to fit different sorts of arch models containing different orders. So let's say arch 2, arch 3, probably arch 4, arch 1, right? And from this entire plethora of different arch models, you pick the one, or rather fix the order whichever corresponds to the least information criteria. So be it AIC or BIC. Okay. But lastly, you have to make sure that the fixed order, or rather that particular arch model, suits the data well, right? And how do you do that? So examine the PACF of the squared residuals. Okay, so examine the PACF or partial autocorrelation function. So you can always have a graph of that, right? So examine the PACF of the squared residuals, and when you examine the PACF of the squared residuals, peaks in the PACF indicate significant lags which correspond to the arch order. So again, I will say that the step 4 is just to double check that the order that you fixed from step 3 rather makes sense or not, right? And then how do you do that? Again, just to summarize, that you create that PACF of the squared residuals, and wherever you see peaks in the PACF, those peaks indicate significant lags which correspond to the arch order. Make sense again? Okay, so now we will shift attention to a slightly advanced kind of a model. So we are shifting our attention from a very general sort of arch model to an extension of that, which is called as GARCH model, right? And again, as discussed in the last section, probably, that what exactly is the full form of GARCH? So full form of GARCH is nothing but generalized autoregressive conditional heteroscedasticity, or rather generalized arch. Okay, and of course, GARCH would be a suitable extension of arch model. So even the last session we saw that the arch model has some limitations as well, right? So how do you counter those limitations? So of course, one can actually implement a suitable GARCH model or its extension. So probably in the next session we will see that what all extensions are possible of a very general GARCH model as well. Okay, so again this is a very summary kind of a slide that, so again just to summarize the full form, so GARCH stands for generalized autoregressive conditional heteroscedasticity. It's not, now again the idea is that how do you model the changing variance, okay? And the GARCH model is nothing but an extension of the arch model, as discussed before as well, that adds an autoregressive component to the conditional variance, allowing for more flexibility and efficiency in modeling time series volatility. Okay. So what sort of is the extra portion in the GARCH model is that firstly, GARCH is nothing but an extension of arch model that adds an autoregressive component to the conditional variance, okay, allowing for more flexibility and efficiency in modeling time series volatility. Secondly, the GARCH model captures both the past variances and the past squared residuals. So it has two components rather. So the GARCH model captures both the past variances as well as the past squared residuals. So you have to sort of encounter or take part of both the past variances, so its own lags, and the past squared residuals. So lags of ET square as well. Okay. So again, the GARCH model captures both the past variances as well as the past squared residuals, which is particularly useful in financial time series where volatility tends to cluster. Okay. Now again, one very useful sort of an application of this entire arch modeling or GARCH modeling could be seen in financial literature, right? So how do you model, let's say, volatile time series, or again volatile time series is kind of very widely applicable or rather seen in finance literature. So let's say again, just to give you a short example, that if you are observing a stock price and suddenly the stock price sort of jumps due to some event, let's say it has a lot of fluctuations in between. So again, we can safely assume that the overall variance is not constant. So how do you model for that? Okay, and henceforth one can put forward a suitable arch model or a GARCH model, etc. Okay. Okay, so now we will study briefly as to what the model structure is and then how is it exactly different from an arch model. Okay. Now firstly, you should understand that a GARCH model contains two orders, so P comma Q. Okay. So we will specify a GARCH model with orders P comma Q. Model specifies the conditional variance sigma t square as, so this is the equation for capturing the conditional variance. So sigma t square equals omega plus summation I going from 1 to q, so the second order is q, alpha I epsilon t minus I square plus summation j going from 1 to p, beta j and then sigma t minus j squared. Okay. And then again this is a brief summary of all the notations which are involved in the previous equations. Now again you may pause the video and then try to sort of understand as to how this GARCH model is sort of behaving, and then how exactly is it different from a arch M model or rather arch Q model, etc. So again the very important part here is that the GARCH model contains two different and disjoint sort of summations. So the first summation contains this error square terms or rather squared residuals, and the second summation contains the past lags or rather the past values of the conditional variance itself. Make sense? So epsilon t is nothing but the residuals from the mean equation. So whatever mean equation you fit, let us say using ARIMA model or ARMA model, whatever. So epsilon t denotes the residuals obtained or rather extracted from that mean equation. Sigma t square as always is nothing but the conditional variance at time t. Omega serves as an intercept. So omega, which is assumed to be positive, is the constant term. Alpha i's are the coefficients for past squared residuals. So by the way, this is the arch effect or rather the arch terms, right. So again if you go back to the arch equation, so arch equation does not contain the second term that we have here, right. So this term is sort of extra here in the GARCH. Okay. So again alpha i's are nothing but coefficients for past squared residuals which correspond to the arch terms, whereas beta j's are nothing but the additional coefficients for past variances which correspond to the GARCH terms. Okay. So this entire first set or the first summation correspond to the arch equation, and this entire second set correspond to the GARCH equation. And again lastly P and Q, what are they? So P and Q are nothing but the order of the GARCH and arch terms respectively. Okay. So P corresponds to the GARCH order and then Q corresponds to the arch order. Make sense so far hopefully? Okay. So again just to summarize very quickly, so sigma t square is dependent on some constant term plus some arch terms, and then again arch terms are what? So arch terms correspond to nothing but the lags of the squared residual, so epsilon t minus I square and multiplied by some coefficients, let us say alpha I, and plus you have several GARCH terms, and then GARCH terms contain the past lags of the conditional variance itself. So sigma t minus j square multiplied by coefficients which are denoted by beta g. Okay, so now we will study very briefly as to what are some of the important key features of this GARCH model, right. So the very first feature is called as volatility clustering, and again I am very sure that we have covered this the first point several times in the last couple of lectures as well, right. So what do you mean by volatility clustering is that models periods of high and low volatility commonly observed in financial data. But again in short, volatility clustering means that periods of high volatility are followed by the same sort of a period, and periods of low volatility are followed by low volatility. Okay. So this phenomena is called as volatility clustering. Secondly, mean reversion. So what do you mean by mean reversion? So mean reversion is implied when summation alpha I plus summation beta j is strictly less than 1, meaning volatility eventually reverts to a long term level. Okay. So under this condition, that summation alpha I plus summation beta j, if you simply add all the coefficients, right, is strictly less than 1, this means that eventually the volatility or changing variance would revert to a long term level. Okay. I will give you a very short example in this regard, that let us say that even though you will see drastically changing variance initially, let us say something like that, right, but later on the variance has to converge to some long term sort of a constant, something like that. Okay. And then this tendency in the volatility is called as mean reversion. And lastly, leverage effect. So what do you mean by leverage effect? So standard GARCH cannot handle asymmetries like negative shocks affecting volatility more than positive shocks. Okay. So let us say for some reason if the negative news or let us say negative shocks affect the changing variance or volatility more than positive news or positive shocks, then a simple arch model or a simple GARCH model cannot handle such asymmetries, and for that you require all sorts of extensions which we will study in the next lecture. But these are a couple of extensions. So let us say eGARCH or GJR GARCH, right. So extensions like these address this phenomena which is called as leverage effect. Okay. So these are some shortcomings when it comes to GARCH modeling, or some of the key features when it comes to GARCH modeling. Now this slide I have tried to put just to sort of summarize this entire idea and do sort of brief you about the steps to fit a GARCH model. So how exactly can one fit a suitable GARCH model to a data? Okay. So, again the very first step is you have to always perform the arch effect test to confirm the presence of conditional changing variance or heteroscedasticity. So, the very first step is to always perform the arch effect test using, so one can use the LM test for that on the residuals. Okay. Then the second step is to use module selection criteria like AIC, BIC to decide on P and Q. Okay. Then thirdly, one can use MLE, so let us say maximum likelihood estimation, to fit the GARCH models. Then check the diagnostics. So, what do you mean by diagnostics? So, for example, residual should have no arch effects, that is, residual should be completely homoscedastic, right. I mean, once you fit the GARCH model, then you obtain the residuals of that GARCH model, and then residual should not have any more arch effects, obviously. Okay. And lastly, use the fitted GARCH model to forecast the future variances and any conditional volatilities. Okay. So, this is sort of a walkthrough as to how can one sort of fit a suitable GARCH model, where you have to first confirm that whether arch effects are there or not, then use some model selection criteria like AIC or BIC to decide on the orders P and Q. Then you have to estimate all the parameters. So, one can make use of MLE estimation here and check the diagnostics. So, check diagnostics is always there rather, which is nothing but diagnostic checking we always do, right, after the model fitting. And lastly, forecasting. So, use the fitted GARCH model to forecast some future variances and conditional volatilities. Okay. So, in short, if you want to specify what exactly or how exactly does a GARCH 1-1 model look like. So, I have just presented this slide here just again as a summary. So, the GARCH 1-1 model is one of the most commonly used models for volatility modeling in time series data. And what it does is that it extends the basic arch model by incorporating lagged conditional variances in addition to lagged squared residual. So, again the entire idea is same, the only thing is, so P happens to be 1 here and then Q happens to be 1 here rather. So, this is nothing but the mean equation. So, YT equals mu plus epsilon t, and epsilon t also comes in the second equation where you are trying to model the variance. So, sigma t square happens to be equal to omega plus alpha into epsilon t minus 1 square plus beta into sigma t minus 1 square. Okay. So, this is a very simplistic looking sort of a GARCH 1-1 model, which is again a very common model which is used to model any real life data. Now, firstly, what exactly are the key properties of the GARCH 1-1 model? So, again I will say that these key properties exactly are sort of similar to some of the key features we studied for a general GARCH PQ model, right. The first is again the same, so volatility clustering. So, models periods of high and low volatility commonly observed in financial data. Second one is again the same, so mean reversion. So, when does mean reversion happen? Whenever this condition is met. So, summation alpha I plus summation beta j, if it is less than 1, then the overall volatility eventually reverts to a long term level. And thirdly, stationarity. So, again on top of that, if this condition is as well met, that if alpha plus beta is less than 1, for example, in GARCH 1-1 model you only have 2 coefficients, right. So, you do not have summations here, right. So, again if you go back a slide, so you do not see any summations here, and why is that? Because both the orders are 1, isn't it. So, you do not have any summations here. So, you only have these 2 coefficients to focus on, so alpha and beta. Okay. So, if it happens that if alpha plus beta is less than 1, the model is stationary. On the other hand, if alpha plus beta is really close to 1 or almost equal to 1, then the volatility exhibits some long memory or persistence. And again I am very sure that by this time you should know that what do you mean by long memory. So, we had an entire week where we discussed what do you mean by long memory, persistence in the underlying time series and all. Okay. So, these small conditions pertaining to a GARCH 1-1 model could either mean mean reversion or stationarity, and on the other hand, if alpha plus beta is very close to 1, then the changing variance exhibits some long memory or persistence properties. Alright, so now towards the end we will sort of wrap this week by discussing few practical applications. Okay. And again the practical applications could be seen in multiple different areas. So, the first one is let us say financial markets, in let us say asset price modeling. So, what is the objective here? So, objective is to model the volatility of returns for assets like stocks, bonds, currencies, etc. Okay. A small example in this regard is that predicting volatility in stock prices or cryptocurrency returns for let us say trading strategies. Okay. And what is the impact of that? So, helps traders optimize some risk return trade offs in high frequency trading. Okay. So, the first example could be seen in financial markets pertaining to, let us say, asset price modeling. Again, a second example in financial markets could be in relation to option pricing. So, how exactly? So, the objective here is nothing but compute the implied volatility used in pricing options. Example, GARCH models are integrated into the stochastic volatility models for dynamic pricing, let us say in Black-Scholes type of frameworks. And what exactly is the impact? So, provides a better understanding of changing variance or the skew observed in the markets. Now, this is a slightly different sort of an example coming from a risk management point of view. So, value at risk. So, value at risk, or in short VAR, is a very common kind of a metric to capture the extremes of the risk measures. So, the objective here is to estimate the risk of portfolio loss over a certain time horizon. For example, banks use GARCH to compute the value at risk considering time varying volatility. And what is the impact? So, critical for compliance with regulatory requirements like Basel III records and so on and so forth. So, by the way, Basel III records come under the compliance framework, or rather the regulatory framework. And lastly, stress testing. So, again coming under the risk management heading. So, stress testing, the objective is to simulate worst case scenarios by considering periods of high volatility. One small example is analyzing portfolio behavior during financial crisis, etc. Okay. So, this sort of sums up the idea behind, let us say, the extension of ARCH, which is called as GARCH model. Now, in the next session, so next session would be the last theoretical session this week, we will try to extend this a step ahead and then try to incorporate lot of extensions of a general GARCH model. And then the idea behind that is that each and every extension we study in the next lecture would be suitable to sort of model and put forward some practical application in a different manner. Okay. Thank you.